Go through any introductory calculus textbook and you're going to find this problem in related rates. The falling or sliding ladder problem. However, this problem is actually really bad. Doing a little experiment with the pen representing the ladder, when the ladder falls, we see that it doesn't perfectly slide down against the wall and that there's some distance. So let's set up the problem in its most general form. A ladder L feet long leans against a vertical wall. If the base of the ladder is moved outwards at the constant rate of k feet per second, how fast is the tip of the ladder moving downward? Translating this into the language of derivatives, we have dx dt equals k and ladder length L. We can draw a picture representing the problem, which provides us with a right triangle modeling the situation. We solve this problem by applying the Pythagorean theorem in implicit differentiation. Doing so, we get x squared plus y squared equals L squared. Our first step is to differentiate both sides with respect to t. Remember to apply the chain rule here. From the setup, we have k equals dx dt. Since the ladder is not changing length, dl dt is 0. Finally, we solve for dy dt. Doing so gives us dy dt equals negative kx over y. Performing some analysis on this differential equation, we note that for small y, dy dt is going to blow up. In fact, if we let height y equals kl over the square root of c squared plus k squared, we get into some serious trouble. At this height, the tip of the ladder is moving at the speed of light. So let's do an example with some values. If we were to have a leaning ladder on a building, say the Empire State Building at 381 meters, with a base of 100 meters, the Pythagorean theorem gives us a ladder length of 394 meters. For a slipping ladder, the ladder follows circular motion constrained by the Pythagorean theorem. The time it takes for a top end of the ladder to fall from height h0 to the ground is given by 2/3 square root of h0 over g. When we plug in our values, we get about 4.15 seconds. Oversimplifying a bit, the average velocity is given by a change of height over t. With our values, we get 91.8 meters per second equals k. Using the formula we had from before, we plug in these values, and we get y equals 1.17 times 10 to the negative 4, or 0.117 centimeters. At this height, if the ladder is still against the building, the top of the ladder is moving at the rate that is the speed of light. You can verify this by plugging in the values back into the original equation, with x being 394 meters, because it is almost, by a small amount, the entire length that has reached the ground. Falling ladders did not become relativistic in real life, so this calculus-related rates problem is flawed, and so we're now going to show the correct better model. To work this through, we are going to examine some differential equations governing the situation of the moving ladder being supported by the wall and an unsupported ladder behaving as a stick pendulum. In the stick pendulum, some rotational mechanics come into play. Applying Newton's second law of motion to rotation, it states that if a rigid body rotates in a plane about an axis moving with uniform velocity, the total external torque acting on the body is equal to the product of its moment of inertia and angular acceleration, where both the torque and moment of inertia are calculating relative to this moving axis. Writing it down, we have the sum of torque tau is I, the moment of inertia, times alpha, its angular acceleration. This is a model of the rotational situation. The only forces on the freely falling ladder are the upward force from the ground at the pivot point, which produces no torque, and the gravitational force, which provides the same torque tau as a force of magnitude mg acting downward at the center of mass of the ladder. Thus, the sum of the torque tau is equal to mg L cosine theta over 2, which from before is equal to I alpha. The torque here is positive as we set up our coordinate system moving counterclockwise. Next up, we need to find the moment of inertia I of a uniform rod, an oversimplification representing a ladder with mass m and length L about its endpoint is equal to this: 1/3 ml squared. This is a moment of inertia of a uniform rod rotating about one end. The angular acceleration is given by taking the second derivative of a supplementary angle, that is, the angle pi minus theta. Thus, the angular acceleration alpha between the ground and the ladder measured counterclockwise is the second time derivative, negative theta double dot. By using Newton's second law of rotation, the sum of the torque is equal to I alpha, we can thus equate the following. And when we solve for theta double dot, we get the criteria for when the ladder loses contact with the wall. Next up, we're going to find theta double dot for when the ladder is in contact with the wall. Drawing the right triangle, we have the height y is equal to L sine theta. Taking the derivative, we get y dot is equal to L cosine theta, theta dot, which is equal to x theta dot. Then plugging back into differential equation modeling the ladder, we get theta dot is equal to negative k over L sine theta. When we take its second derivative, theta double dot, we get this nasty mess. Let's plot the second derivative, theta double dot, versus theta for L equals 41 feet, k equals 10 feet per second, and g equals 32 feet per second squared. The blue represents contact with the wall, and the orange represents no contact, or the pendulum model. Graphing these two, we see that there is a critical angle where the ladder is held up by the wall, but after the theta c, it is free to behave as a stick pendulum. With these L, K, and G values, we get theta c is equal to 0.38. Looking more at a critical condition for ladder wall contact, we equate the equations for theta double dot, and simplifying it down, we get this. Since sine can be at most 1, we have the following inequality, and when k is greater than square root of 3 over 2 GL, it is impossible. Otherwise, since y critical is equal to L sine theta critical, we have yc is equal to this. So this is the correct critical height after applying mechanics. Our next step here is to find the path of the ladder's tip after it leaves the wall. This is the often neglected part in the standard calculus problem, but it's fun to explore what the math tells you. So here's a diagram. At the moment of separation, the base is at x critical, with angle theta critical. xc is moving, and xc is given by L cosine theta c. So the distance from the wall to the upper end of the ladder will be d is equal to xc plus kt minus L cosine theta at this time. It's xc plus kt because the base moves at constant speed k. Additionally, by the figure, we have yt is equal to L sine theta. From before, we have theta double dot for losing contact with the wall, and we also have our initial values. First, we have theta 0 is equal to theta critical, which is arcsine of the cube root of 2 squared over 3gl. And this comes from a sine cubed theta c equation. Next up, we have theta dot 0, which is equal to theta dot c, which is equal to negative k over L sine theta c. Using the same values from before, L equals 41 feet, k equals 10 feet per second, and g equals 32 feet per second squared. Plugging in these values, we get theta 0 is approximately 0.379428. And remember, this is equal to theta c. Similarly, for theta dot 0, this is approximately negative 0.658503. And remember, this is theta dot c. So these are our initial values for the differential equation. Going back up, we need to find theta t by working through this differential equation from our initial conditions. With theta c given from above, we can now get yc, which is L sine theta c. And with our values, this gives us the critical height of 15.19 feet. So now what we need to do is find the impact. This is our distance d, which we do not know yet. D is to be determined as we need theta t, which is really hard to find analytically. So we need to use a
numerical method.
Numerical method.
How the heck do I get theta t?
Second-order nonlinear differential equation.
I will be using Wolfram Mathematica. Here in Mathematica, we set our initial conditions of the values of g, L, and k, as well as theta critical. Next up, we use ND-solve and plug in our theta double dot condition. We have the initial position of the base, xc, create the parametric functions to model distance and y height. Next, we need a time of impact for when the ladder hits the ground, which is just root finding. We set up the plot of theta t versus t so we can see the time of impact, and we also see the parametric plot of the graph. So right now we see our values. The impact occurs at 0.42 seconds, and using this numerical method to find the distance d, we get about 1.32 feet. This is a distance that follows after reaching the critical angle theta c, changing regime to act like a stick pendulum. So what's next with this bad problem? This should be the status of the falling ladder problem in introductory calculus text. The easiest thing to do here is to remove such problems from textbooks. Or instead of asking for y dot, ask for x dot for a falling ladder under the force of gravity with no friction at either end. But this is better left as a physics mechanics problem. Or we can leave problems like this in the text, but ensure that exercises have k less than or equal to the square root of 3 over 2 GL, and ask for y dot when y is larger than yc, so that the standard approach rings true physically. Mention as a marginal note that the standard model breaks down once y is less than yc, or if k is greater than or equal to the square root of 3 over 2 GL. This video is based on a journal article, The Falling Ladder Paradox, by Paul Schulten and Andrew Simonson from the January 1996 issue of the College Mathematics Journal. If you would like to read more about it, I have left a link to it in the description below. Thanks for watching.